Right now, somewhere in the universe, time is running slower than it is for you. Not metaphorically, not as a figure of speech. Literally slower, measurably, mathematically slower, the same way a river runs slower through a wide, flat plain than it does through a narrow gorge. This isn't a fringe idea or a thought experiment confined to chalkboards. It's been measured directly here on Earth using atomic clocks precise enough to detect fractions of a second of difference over the course of a single day. Fly one of those clocks on an airplane, or place one at the bottom of a tall building instead of the top, and it will read a slightly different elapsed time than an identical clock left undisturbed. Time, it turns out, was never quite the single universal ticking clock our everyday experience makes it feel like. And if you push that idea to its absolute extreme, you arrive at a genuinely strange question. Could time actually stop? Not slow down. Not pause for a moment. Stop completely forever in some specific place, or perhaps even across the entire universe, given enough time. The honest answer involves black holes, the death of every star in existence, and a debate among physicists about whether time can ever truly end at all, or whether the question itself is built on a mistake. By the end of this two-part video, you'll understand exactly what physics currently has to say about it. Let's get into it. Before we can ask whether time can stop, we need to be honest about something uncomfortable. Physicists don't fully agree on what time actually is in the first place. At the most basic level, the equations describing individual particles and forces are almost entirely symmetric with respect to time. Run the equation for two billiard balls colliding forward and it works. Run it backward and it still works, mathematically just as well. Nothing in the fundamental laws of motion insists that time has to move in only one direction. So why does it feel like time only ever moves forward for us? The answer comes from a completely different branch of physics, thermodynamics, and specifically a quantity called entropy. Entropy is, roughly, a measure of how many different microscopic arrangements correspond to the same overall large-scale state. A tidy room has very few arrangements that would still look tidy. A messy room has an enormous number of arrangements that would all look equally messy. There are always vastly more disordered arrangements than ordered ones, which is why systems drift toward disorder over time, purely as a matter of overwhelming statistical odds, not because some force is actively pushing them there. The universe itself began in an extraordinarily low entropy state, the hot, dense, remarkably uniform condition immediately after its earliest moments. Since then, entropy has been steadily climbing, and physicists believe this one-directional climb is the actual reason time feels like it has a direction at all. We remember the past and not the future because the past, by definition, had lower entropy. The arrow of time isn't a separate law bolted onto physics. It may simply be a consequence of which direction entropy happens to be increasing. This is a genuinely strange idea to sit with. It means that if you dropped a glass and watched it shatter, nothing in the underlying laws of physics actually forbids the pieces from spontaneously reassembling and leaping back into your hand. It's allowed. It's just staggeringly improbable because there are vastly more ways for the pieces to be scattered than for them to be arranged into an intact glass. We never see it happen, not because it's against the rules, but because the odds are so overwhelmingly stacked against it that the age of the universe isn't nearly long enough for it to be likely. If time's flow is tied to physical processes rather than some independent universal clock, then it makes sense that it can run at different rates in different places. And we've actually measured this directly in exactly the extreme environments you'd expect, near massive objects and at very high speeds. Einstein's general relativity tells us that gravity itself slows time down. A clock sitting near a massive object deep in a strong gravitational field ticks measurably slower than an identical clock far away in weaker gravity. This has been confirmed with atomic clocks. One sitting at the base of a tall tower runs very slightly slower than one at the top, exactly matching Einstein's predictions. In an effect so precise it has to be corrected for in the software running GPS satellites every single day. Now take that effect to its most extreme possible setting, a black hole. As you approach the event horizon of a black hole, the boundary beyond which nothing, not even light, can escape, Time dilation due to gravity becomes more and more severe. From the perspective of a distant observer watching someone fall toward that horizon, something remarkable happens. The falling observer appears to move slower and slower as they approach the boundary, their image growing dimmer and more red-shifted, seemingly taking an infinite amount of outside time to actually cross the horizon at all. In practice, this means a distant observer would never actually witness anything crossing the horizon. The light carrying the image of the falling object would stretch out to longer and longer wavelengths and grow dimmer and dimmer until it faded below the threshold any real telescope could detect, leaving behind what looks, for all practical purposes, like a faint, frozen imprint on the black hole's boundary rather than a clean, final crossing. From the distant observer's point of view, it's almost as if time for that falling object is grinding to a halt, approaching a full stop but never quite completing it, stretched out toward an infinite delay that never technically finishes. Here's where the story gets genuinely strange, because that frozen, slowing down picture is only true from the outside observer's perspective. For the person actually falling toward the black hole, nothing about their personal experience of time changes at all. From their own point of view, they cross the event horizon in completely ordinary finite time. Their watch keeps ticking normally. They don't notice any slowdown, any freezing, any hesitation at the boundary, because from their frame of reference, there's nothing special happening there at all. The freezing effect only exists in the mathematics describing how a distant external observer would perceive events stretched out and redshifted by the extreme gravity involved. It says nothing about what time is actually doing for the person experiencing the fall themselves. This distinction matters enormously for the question we're building toward. It shows that time stopping isn't necessarily one single universal fact about reality. It can be a matter of perspective, a description of how a signal or an observation behaves as it tries to escape an increasingly extreme gravitational environment, rather than time itself literally ceasing to exist for whoever is experiencing it directly. It's a bit like watching someone walk away from you down an infinitely long hallway that keeps stretching further every time they take a step. From where you're standing, they never quite reach the end. They just keep getting smaller and slower forever. But from their own perspective, they're just walking normally, one ordinary step after another, completely unaware that the hallway behind them is doing anything unusual at all. But this raises an even bigger question. If time near a black hole can appear to freeze from one point of view while continuing normally from another, what happens on the largest possible scale, not for one falling object but for the entire universe? Once every star has burned out and every black hole is evaporated, could time in that final state actually stop for real with no exception and no observer left to see it differently? In part one, we saw that time's flow seems to be tied to entropy, and that gravity can slow it down so severely near a black hole that it appears to freeze entirely from an outside observer's point of view, even though for whoever is actually falling, nothing about their own experience of time changes at all. That distinction between the outside view and the inside experience turns out to matter for everything that follows, because it means time stopping was never a simple single fact about the universe to begin with. It depends on who's watching from where and under what conditions. Keep that in mind, because we're about to apply the same kind of question to the largest possible stage there is. Not one falling object near one black hole, but the entire universe, taken as a whole across the full span of its future. Now let's ask the bigger question. What happens to time on the scale of the entire universe once everything else is finished happening? We know that entropy, left alone, only ever increases. And we know the universe is finite in its available energy, even if it's vast in its available space. Put those two facts together, and you arrive at a genuinely strange endpoint, a state of maximum entropy, sometimes called heat death. Stars are not a renewable resource. They form from clouds of gas and dust, and star formation across the universe is already slowing from its peak billions of years ago. Eventually, the last stars will burn out. Even black holes, through an extraordinarily slow quantum process called Hawking radiation, will eventually evaporate over timescales so long they make the current age of the universe look like a single passing second by comparison. Once that happens, what's left is a universe with no meaningful energy gradients left to do any kind of work. No structure, no chemistry, no stars, no light, no motion worth the name. Just an extremely thin, extremely cold, maximally disordered scattering of particles spread across an unimaginably vast, ever-expanding space. To put the timescale in perspective, the current age of the universe is roughly 8 billion years. The point at which the last dimmest stellar remnants finally exhaust themselves is expected to unfold over trillions of years. The evaporation of the largest black holes through Hawking radiation is projected to take a span of time so vast it's typically written using exponents rather than ordinary numbers, a duration that makes the entire history of the universe so far look, by comparison, like the very first fraction of a second. And here's where our question becomes unavoidable. If the arrow of time is driven by increasing entropy, and entropy has nowhere left to increase to, does time itself simply stop mattering at that point? Not stop existing necessarily, but stop having any meaningful direction, since the very thing that gave it a direction has run its course completely. This is genuinely one of the more contested questions in theoretical physics, and different physicists lean toward different answers. One school of thought holds that time without change is essentially meaningless, that time isn't some independent backdrop ticking along, regardless of what's happening in the universe, but is instead defined entirely by the relationships between changing physical states. Under this view, a universe with no possible change left to undergo wouldn't just have time slow down. It would, in the most meaningful sense that matters, have time stop, because there would be nothing left for time to measure. A clock with nothing left to tick against isn't really keeping time anymore, even if some abstract mathematical time coordinate could still technically be written down on paper. A different perspective argues that even in a maximally disordered heat death universe, time doesn't fully stop, because true maximum entropy is never quite reached. The universe simply approaches it asymptotically forever the way. A curve can get closer and closer to a line without ever quite touching it. Under this view, extraordinarily rare quantum fluctuations could still, in principle, occur even in the emptiest possible universe, meaning some faint trace of things happening, and therefore some faint trace of a meaningful arrow of time never fully disappears, no matter how long you wait. Some physicists have even pointed out that these rare fluctuations, stretched across an effectively unlimited span of time, could occasionally and randomly assemble complex, orderly structures out of the surrounding near emptiness. Purely by chance, the same way shuffling a deck of cards long enough will eventually, purely by luck, produce a perfectly ordered sequence. This remains a genuinely strange and unsettled corner of theoretical physics, but it illustrates the core disagreement clearly. One camp sees heat death as an effective stopping point for anything meaningful happening at all, and the other sees it as an endless, almost imperceptibly slow simmer that technically never finishes. Neither position has been definitively settled, and it partly comes down to a genuinely philosophical question sitting underneath the physics. Is time a fundamental feature of reality in its own right, or is it an emergent description of change, one that simply stops applying once change itself becomes rare enough to be meaningless? There's one more idea worth including here, proposed by the mathematical physicist Roger Penrose, because it offers a genuinely different answer to the entire question: what if heat death isn't actually the end of the story at all? Penrose has proposed a model called conformal cyclic cosmology, which suggests that a universe stretched out into an extremely thin, cold, near-empty state at maximum entropy might, under certain mathematical conditions, become indistinguishable from the extremely hot, dense, uniform state the universe began in. The key insight behind the idea involves what's called conformal geometry, a way of describing shapes and structures that ignores absolute scale entirely, caring only about angles and relative proportions. Penrose noticed that described this way, an infinitely stretched out, cooled down universe and an infinitely compressed, superheated one can end up looking mathematically identical, even though intuitively they seem like polar opposites. In Penrose's proposal, the geometry of an infinitely expanded, maximally diluted universe could be mathematically reinterpreted as the starting point of an entirely new cosmic cycle, a new expansion beginning again from what looks, from a certain angle, exactly like a fresh beginning. Penrose has even pointed to faint circular patterns in the cosmic microwave background as possible, though highly contested, evidence of an earlier cycle leaving a subtle imprint on our own, a claim that most cosmologists remain skeptical of, since the patterns identified so far haven't held up consistently across independent analyses of the same data. This remains a genuinely speculative model without confirmed observational support, and it hasn't displaced the standard heat-death picture as the mainstream expectation. But it's worth including because it reframes the entire question we've been asking. If Penrose's proposal, or something like it, turned out to be correct, then time wouldn't stop at heat death at all. It would simply reset, folding the ending of one cosmic era directly into the beginning of the next, with the arrow of time picking right back up where an entirely different observer story might just be starting. So can time stop forever? The most honest answer physics can currently give is, it depends entirely on what you mean by time. From the outside, near a black hole, time already appears to freeze, stretched into an infinite delay that never technically resolves. On the scale of the whole universe, heat death represents a state where the very thing that gives time its direction, increasing entropy, finally runs out of room to increase, leaving physicists divided over whether that counts as time stopping or simply time losing its meaning. And there's at least one serious proposal suggesting that even that ending might secretly be a beginning, folded back into a new cycle we don't yet have the evidence to confirm or rule out. What's clear is that time was never quite the simple, universal ticking clock our intuition assumes it to be. It's tangled up with gravity, with entropy, and possibly with the entire shape of the cosmos itself, which means the question of whether it can stop was never really a simple yes or no question to begin with. If untangling the universe's strangest questions is your kind of thing, subscribe, because there's a lot more still left to figure out.